Today is mostly going to be a discussion on the concepts of singularity and residue for an analytic function. So just as a kind of overview of what we've done so far, we've developed a pretty solid theory for analytic functions on simply connected domains of the complex plane. So in the global sense, so our integration theory for such functions is good. So we know that on simply connected domains, your analytic function has to have an antiderivative, and that the integrals over closed curves always give 0, and consequently that you have path independence of integration as well on this domain. So having antiderivatives, so you can compute integrals like in calculus. If you have an antiderivative, it's like you're doing the fundamental theorem of calculus part 2, and it doesn't matter which path you take between 2 points in your simply connected domain, you always compute the same integral. So there's a pretty robust theory of integration for analytic functions. And we also know that locally, our differentiation theory of such functions is good, and it's so powerful that we even have a local power series representation for a function. Okay, so that's so especially the integration stuff is for simply connected domains. But many analytic functions, I should say, naturally have non-simply connected domains. For example, the function 1 over z has the non-zero complex numbers as domain, and that's not simply connected because say unit circle, a curve going around the unit circle, encloses a point not in the domain. So that is not a simply connected domain. And more generally, you could look at something like this f of z here, 1 over z minus z1 dot 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 z minus zn. And these are examples of rational functions. So you can think of rational functions more generally whenever you have an interesting denominator, wherever the denominator is 0. That's not going to be in the domain of your analytic function. And so you're going to have a non-simply connected domain. And so since these functions are entirely natural and ubiquitous, we would like to know to what degree can we develop our theory to more fully incorporate these singular points, like the origin for 1 over z, or these z sub i's for this other, the place where rational functions where the denominator is equal to 0. Okay. And so the starting point of the theory for analytic functions was Cochise theorem, the integral over a closed curve. If your closed curve contains if the interior of the closed curve is contained in the domain, then an integral over that closed curve gives 0. So what we would like to do first is have some generalization of Cochise theorem that incorporates the situation that's illustrated here, where you have an analytic function and it has some singular points. So think like this rational function here, right? It has a bunch of points not in the domain of the function, and then you have this curve in the domain that encircles those. Some of them or all of them encircle those singular points. And what can we say about the integral over that curve gamma that's encircling those singular points? So is there anything interesting we can say about that? Well, how did we initially prove Cauchy's theorem? So if you remember back, our first proof of Cauchy's theorem was in the case when f prime, assuming f prime is continuous, which of course we know now we don't have to assume that. Analytic function, automatically the derivative is continuous. but we assume that the derivative was continuous, and then it was just an application of complex Green's theorem, right? So you have a closed curve, and the domain and the interior of that curve is contained in the domain of your function. You just turn this line integral around the curve gamma into a surface integral, and that or an area integral, and that area integral, the integrand is 0 when the Cauchy-Riemann equations are satisfied. And if those partial derivatives are continuous, you can do that integration, so Green's theorem is valid, and you just get 0. So that was the proof of Cauchy's theorem initially. So if we try to mimic something like that in this situation, so let's say we're in the following situation. Assume gamma is a typical curve in the domain of F, and F is analytic on the interior omega of gamma, except possibly at some isolated points let's say Wi. So this isolated means, isolated means there is an r sub I greater than 0 such that the disk around Wi of that radius doesn't contain any W except Wi. So the intersection of this with the set of Wj's is just equal to Wi. The set containing just Wi. So I guess over here to be more clear, this is a collection. Yes, maybe to be less confusing, I'll change that to J over there. So the situation will look something like it does up in the picture up there. And well, it could be that there are an infinite number of points, an infinite number of these W's, but it's easiest to think about it in the case where there's only finitely many. I remember what we're going to do is look to apply Green's theorem to this situation. So let me insert, so these Wi's, right, they're isolated points. That means there's a little disk around each one of them that doesn't contain any of the others. All right, so these are supposed to be disks. I know they look a little bit rough. Okay, and well, what we can do now is we can apply Green's theorem to the region in between here. So we can apply Green's theorem to this region, omega. Well, I guess I already called that omega. So let me think of a different letter. Well, let's just say R for region. Okay, and it'll help to give things names here. So this outer curve, that's gamma. These blue curves oriented like this, gamma 1, gamma 2, gamma 3, etc. And so if we apply complex Green's theorem, so what we'll do is we'll apply it to gamma. So gamma's on the, so you have to remember how to orient this correctly. So gamma is oriented correctly as the boundary of R, but these gamma i's being counterclockwise oriented and in the interior here. So you have to remember that the appropriate orientation for the curves on the inside, so with respect to R, so you have to imagine that R, if you go counterclockwise in R like this, that counterclockwise circle would sort of induce an orientation going this way along one of these gamma i's, and that's a clockwise orientation. So in order to get that clockwise orientation, we're going to take minus gamma 1 minus ... minus gamma n. So that's our boundary of R. The integral of f along that is equal to the integral, double integral, over R times 2i of df dz bar. And since our function is analytic away from those points W, which are inside those disks that we put in there, this is just identically 0, and so that's equal to 0. And that is equivalent to saying that the integral over gamma of f of z dz, taking all these minuses in here and putting them on the other side of the equation, that's equal to the sum over I of integrals around the boundary of these disks of f of z dz. Okay. So this result will be called the residue theorem. And I just realized that in order for this to make sense, to apply Green's theorem and for this sum to make sense, I really should have, I know I said that this could be an infinite number of points, but I take that back. And I don't feel like going back and deleting the video, so I'm just going to add it here. So finite number of. Okay, so we'll be assuming that this curve is going around a finite number of these singular points. Okay, and so the integral over a curve, so the basic takeaway is that if you have a finite number of these singular points for your function, or your function might not be defined, you can turn a line integral around gamma into a bunch of smaller integrals around circles that just enclose those points and only those points. So this reduces the study of an integral of your f around an arbitrary curve gamma into these very special integrals here just around one of these singular points. And as we'll see, these integrals here, it turns out there's a quite simple way to compute this quantity directly that doesn't involve integration. And then this is going to be a great powerful, even practical tool for computing integrals, even real integrals. So it'll be so this theorem contains within it a great practical tool for computing real integrals, because there's a way to turn these general integrals into these more special ones, and then there's an alternate way to compute these special numbers here. So this will allow us to do some integrals that you can't do by ordinary means in calculus. So that's one practical usage of the theorem that we'll see. But before we get into all of that, we just need to, so before we get into these practical applications, agenda is to define and study the concept of singularity, and two, explore the quantity integral of f over the boundary of a small disk around a singular point. Okay, and this quantity is essentially equivalent to what's called the residue of f at w sub I. Okay, so that's what we're doing, and that's why we're doing it. So here's the definition. Let f be analytic with domain D. Then Z0 is an isolated singularity of f if Z0 is not in the domain of D, but f is analytic on the disk around Z0 of some radius, with the exception of Z0 itself for some r. Okay, so you should think about like 1 over z at z equals 0. Okay, so some examples. So one would be like z squared minus 1 over z minus 1 at z naught equals 1. Okay, so you might recognize that this numerator is factorizable as z minus 1 times z plus 1 all over z minus 1. And so technically this function here, z equals 1, is not in the, it's z naught, which is the point 1. That's not in the domain of this function, right? Because you plug it in and you get 0 over 0, which is not a valid output that we accept. But we recognize here that right, if you were to sort of cancel both of these z minus 1s from the numerator and denominator, that this function has the same value as z plus 1 at every z which is not equal to 1, and then in fact extends the original function, because now you can plug in 1 to z plus 1 and get a perfectly valid answer, right? So what's going on here is that basically we just sort of have a bad definition for our function, and it's extendable beyond the original domain to a slightly larger domain. So this point z naught is only a singularity of our function, because we didn't define our function in as optimal a way as possible. It's perfectly possible to redefine it so that it has a larger domain and still makes sense. So in this case, so this is what we're going to call later this is a removable singularity. And so generally speaking, what happens here is that we have good behavior as z goes to z naught here. Right? Because secretly there's a better definition of the function, and as z goes to z naught, there's good behavior so we can define the function at z naught by taking a limit. Right, so if we were to take the limit of this expression as z goes to z naught, we would get 2. So that good behavior allows us to extend the definition of our function to a slightly larger domain and bring z naught into the fold. So it's not really a singularity in some sense. It's only singular because we made a bad choice of how our function was defined. Okay, so that's the first case. Broadly speaking, you have good behavior as you approach the so-called singular point. 2 would be examples like 1 over z, or 1 over z plus 1 over z squared, something like that at z naught equals 0. So in this case, as z goes to z naught, your f of z in absolute value goes to infinity. Right, so your function's blowing up as you go to z naught, blowing up in the sense of the absolute value exploding to infinity. So that's clearly the case here in this 1 over z case, and in this case here, you might wonder whether there's like some interference between the first term and the second term, but that's not the case. So this is 1 over z squared times z plus 1. And so this is a perfectly well-behaved and bounded quantity as you go to 0. But this 1 over z squared, that definitely goes to infinity. So these things are both going to infinity. The norm of f of z is going to infinity as z approaches z naught. And this will be called a pole. Okay. And then there's a third case, which is that neither of these two things happens. So e to the 1 over z, for example, and z naught here equals 0. Basically here you have bad behavior as z goes to z naught, but not comprehensibly bad. So this is bad behavior. So this is contra 0.1, but it's not comprehensibly bad, and that's contra 0.2. So basically, this type of singularity is going to be neither of type 1 or type 2. Okay, so your function's not going to remain nice and bounded as you approach the singular point, and it's not going to be that the function's just going to infinity in absolute value. It's going to be some stranger, wilder, chaotic behavior as you approach the singular point, and these are called essential singularities. Essential singularity. Okay. I didn't say much about this e to the 1 over z. So you can think about, so consider x plus I times 0 as that goes to as that goes to 0. So think about approaching the origin along the real axis, and also think about approaching the origin along the imaginary axis. Then you have e to the 1 over x, right? So as x goes to 0, 1 over x goes to infinity or negative infinity, depending on how you approach 0. And then e to the infinity is infinity, and e to the negative infinity is 0. So you have so you have either infinite quantity or a finite quantity, depending on how you're approaching 0. It's not, the magnitude is not uniformly going to 0, independent of how you're approaching 0. So this goes to either infinity or it goes to 0. And then you have e to the 1 over iy. That's e to the negative I over y. And this lies on the unit circle and doesn't approach anything. So this limit does not exist as y goes to 0. Because as y goes to 0, you have, right, so this negative 1 over y is your angle in radians going around the unit circle. So negative 1 over y, that goes to that's going to infinity as y goes to 0. And so that angle is spinning around very rapidly and going off to infinity very rapidly in terms of radians. That means you're wrapping around, right? Your radians are increasing to infinity as y is going to 0. So that's just wrapping round and around the unit circle, never going anywhere in particular. So that limit does not exist. So you have this just general chaos, right? So sometimes the limit exists as you approach the origin. Sometimes it goes to infinity. Sometimes it's not doing anything. It's just kind of all over the place. So you get a sense for the different types of behavior of your singularities. So you can have good behavior, you can have bad but kind of understandably bad behavior, and then you can have total chaos. Okay, so analysis of isolated singularities. So that was kind of an informal discussion of the different types of isolated singularities and what you might expect. So corresponding to those types, so there's 3 different cases. So there's 3 cases. So the first one is that the norm of f of z is bounded as z goes to z naught. Okay, so just think about your function is under control as z goes to z naught. And in this case, it's going to turn out that we can actually redefine our function f on a larger domain, which now will include the point z naught. So this will be a removable singularity. Okay, so our hypothesis here, and so one thing you can do with it is if you multiply this function by z minus z naught, since norm f of z is bounded, the z minus z naught is going to drag that to 0 as z goes to z naught. So the limit as z goes to z naught of that is equal to 0. And furthermore, so what that implies is that we can kind of rewrite that as z minus z naught squared times f of z over z minus z naught. And now we can think about this as a difference quotient. So this equals 0. So what this is telling us is that this function here, so in other words, this function, which we'll essentially be calling g of z, this is saying that this is differentiable at z equals z naught. Right, so what we're going to do is define g of z to be equal to z minus z naught times, z minus z naught squared times f of z when z is not equal to z naught. And because remember that z naught is not currently in the domain of f of z, so this definition wouldn't make sense at z naught yet. But then we can define it to be 0 at z equals z naught. Right, and this, by this fact here, this is continuous at z naught. And so this defines a continuous function, but moreover, by this calculation here, right, we actually see that g of z is differentiable at z equals z naught with derivative equal to 0. And it's clearly differentiable away from z naught because f is analytic away from z naught, and we're just multiplying that by a polynomial. So furthermore, so I guess I'll say this is continuous at z naught. Furthermore, it's differentiable near z naught. And that's with derivative equal to 0. So g prime of z naught equals 0. Okay, well, it's a differentiable function, so we can expand it locally in a power series. So locally, g of z equals b naught plus b1 times z minus z naught plus b2 times z minus z naught squared plus ... but g is 0 at z naught, so that tells us that this 0 order term is 0, and the derivative at z naught is 0 as well, so that tells us that b1 is equal to 0. So our g of z is z minus z naught squared times b2 plus b3 times z minus z naught plus ... Right? So this function here, this is analytic, and because it's given by power series, a valid power series. And if we look, so we have g of z. So g of z is z minus z naught quantity squared times this analytic function, but our definition of g of z was that away from z naught, right, that it was equal to z minus z naught squared times f of z. Right? So this tells us that that we must have f of z equaling this power series when z is not equal to z naught. Right? But this power series is valid at z equals z naught. So this is valid at z equals z naught. So in other words, So this b2 plus b3 times z minus z naught plus dot 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 extends f to be defined at z naught. And thus we have removed the singularity z naught, or the singularity at z naught. Okay, so this is the first and simplest, easiest to handle case of a singularity. It's mostly just, you can think of it as coming from a bad case of definition for our function f. We only have to redefine it, and then we get a function which is in fact analytic at z naught. So if our function is bounded as z goes to z naught, in fact, the limit as z goes to z naught of f has to exist. And then we can use that limit to redefine our function at z naught, and then that redefinition is still analytic. Okay, case 2. So case 2 is that the limit as z goes to z naught of the norm of f of z is equal to infinity. So no matter how you approach z naught, the absolute value of your f is becoming arbitrarily large. All right, so in this case, what you do, the trick is to look at g of z, which is defined to be 1 over f of z. And then, so what you can notice here is that, so g of z is defined near z naught, but not at z naught. However, if we look at the absolute value of g of z, this must be bounded near z naught. Since the limit as z goes to z naught of norm of g of z, that's 1 over the norm of f of z, so that's 1 over infinity, quote unquote, and that's 0. Right? So since g of z is getting near 0 as you go to z naught, it has to be bounded, right? So eventually it has to be inside, say, the unit disk. Right? If eventually it's close to 0, eventually it has to be inside the unit disk. So g of z is going to be bounded there. And well, now we can apply what we learned in part 1 to find out information about g of z. Right, so now apply the analysis of part 1 to g of z. And what we learn there is that we can redefine g so that so that g of z naught makes sense, so that z naught is in g's domain, and furthermore, g of z naught equals 0 necessarily. And that's because of this limit here. All right, so now we have this function g, which is analytic near z naught, and has a 0 at z naught. So thus, z naught is a 0 of g. Now let m greater than or equal to 1 be the order of the 0 of g at z naught. And write g of z equals z minus z naught to the m times h of z, where h is analytic and h at z naught does not equal 0. Then f of z, that's 1 over g of z, and that's 1 over z minus z naught to the m times h of z. And then we can say that's k of z over z minus z naught to the m. And this k of z is equal to 1 over h of z. And k of z makes sense at least near z naught because h of z is not equal to 0 at z naught. So where k of z is analytic and k of z naught is not equal to 0. Right, because that's equal to 1 over h of z naught. Okay, so the conclusion is that if we have this kind of singularity, so this is called a pole, so this, so we say f has a pole of order m at z naught. So when the norm of f is going to 0 as you approach z naught, it must be the case that this looks like an analytic function divided by one of these simple polynomials, z minus z naught to the m. Okay. So in terms of, so let's see, so in this case, so your f of z is near z naught. It looks like, so you have a power series, so k of z has a power series expansion because it's analytic. And then you're dividing by this z minus z naught to the m, and that is, so you can just multiply through. let's see. So at C M, whoops, we have a C1 here. So at Cm minus 1, you're going to have that over Z minus Z naught. And you're going to have Cm, just Cm. And then you're going to have Cm plus 1 over, whoops, not over. Keep messing this up. Cm plus 1 times Z minus Z naught plus Cm plus 2 times Z minus Z naught squared plus dot dot dot. Okay. And what we can do is we can rename these things. So this C naught, so the C's were the power series coefficients for K of Z. But now we'll rewrite them so that we associate them with F. And so this C naught, so we'll change that, we'll call that A sub minus M. Okay, then over Z minus Z naught to the M. C1 is going to be now A sub minus M plus 1, or whoops, A sub minus M plus 1. Z minus Z naught to the M minus 1 plus dot 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 plus A sub minus 1 over Z minus Z naught plus A sub 0 plus A1 times Z minus Z naught plus A2 Z minus Z naught squared plus dot dot dot. Okay, and this is called the Laurent series expansion of F around Z naught. So this is a new kind of series expansion. So when your function's analytic at a point, you can expand in a series of positive power, of non-negative powers of Z minus Z naught if your function's analytic at Z naught. But if your function's not analytic at Z naught, if you have a pole at your at that point Z naught, then you can expand in this kind of series where you allow a finite number of negative powers of Z minus Z naught. So we'll see this is just a special case. This isn't the full. So there's a more general result about Laurent series, but this is Laurent series expansion for a pole. Okay, so your F here, you can write this as sum of A sub n Z minus Z naught to the n, and this is for n from negative m to infinity. Okay, so this is the Laurent series expansion around the order m pole of F at Z naught. Okay, so that's what happens. So that's what you can say in the case of a singularity that has this behavior here. Okay, so we deduce that it's an analytic function which doesn't vanish at our point Z naught times 1 over Z minus Z naught to the m. And so that implies this new kinds of series expansion for our function f locally around Z naught. All right, so that's the case of a pole. And then the third case is neither. So in this case, neither 1 nor 2 happen. And for right now, we're not going to say anything more than that. So it will turn out in this case that we can write, so that you can write f of z is equal to the sum an times z minus z naught to the n. And this will be from n equals negative infinity to infinity, where an infinite number of the a sub negative j's for j bigger than 0 are not 0. Okay, so the craziness of the behavior as z goes to z naught is due to an infinite number of these negative polynomial powers in the Laurent series expansion of f around our singular point. Okay, so that's kind of a preview of something we'll get into later. All right, some examples. So let's look at f of z is z squared plus 5z plus 6 over z plus 2 cubed. There's a kind of obvious singularity here at z equals negative 2. And so let's look at singularity at z naught equals negative 2. So what kind is it? Well, let's see. So could it possibly be removable? So in the case of a removable singularity, we saw that the characteristic thing is that your f of z is bounded near the singular point. But in fact, in that case, we showed that bounded, that implied that the limit as z goes to z naught exists. So the characteristic signature of a removable singularity would be that the limit as z goes to negative 2 of f of z would exist. And so we could easily take a look at that. So like in calculus, the simplest way to see if a limit exists is just to try to plug in negative 2. Right? In the denominator, we get 0, but in fact, in the numerator, we also get 0 in this case. Right? So we get a 0 over 0 limit. Right? If we just plug in. So what we have to do is look a little closer here. And we see that there's a factor of z plus 2 in the numerator. So we have z plus 2 times z plus 3, and then we divide, and this is limit as z goes to negative 2 of z plus 3 over z plus 2 squared, and this clearly does not exist. Right? Because now our numerator is under control, but our denominator, so we get something finite over 0 when we just try to plug in. So this is not a removable singularity. So this is not removable. And this same computation, right? If we look at the absolute value of our f of z, we see that this is the absolute value of z plus 3 over z plus 2. Z plus 2 squared, and so that's absolute value of z plus 3 over z plus 2 squared, and that goes to infinity, right, as z goes to -2, because the numerator is just going to 1. Right, so that tells you we have a pole. And so what's the order? Well, that's easy to figure out, because again, what we do is we write, so our function is not defined at -2, but again, just canceling that factor, we get z plus 3 over z plus 2 squared, and you see that this here, so z plus 3, we call that k of z. This is an analytic function, so k of z is analytic. And when evaluated at the singular point, that does not equal 0. Right? So that's exactly what we had in this case of a pole up here. So our f of z, when you have a pole of order m at a singular point, you can write your f of z as an analytic function which doesn't vanish at that point, divided by z minus z naught to the m. And so the not vanishing at the point, that's a crucial thing. So what we can say here is we have a non-vanishing analytic function at -2 divided by our z minus z naught to the second power. So that second power, that's the order of our 0 at, the order of our pole at -2. Right, so this 2 here, that's the order of the pole. Okay, so the order of the pole is equal to 2. So it's equal to 2. And just to be extra explicit about it, one thing we can do here is we can write everything in terms of z plus 2. So we can write this numerator as 1 plus z plus 2, and then divide by z plus 2 squared. And what we see is 1 over z plus 2 squared plus 1 over z plus 2. Right, so we see explicitly the Laurent series for our function f starting at a -2 power of z plus 2 here. So this is the Laurent expansion of f. So here's another example. So if we look at f of z is sine of z over z. So in fact, it turns out that, so z equals 0 is clearly a singular point. So z equals 0 is an isolated singularity. What kind is it? Well, one thing you can do is, so since we're looking at z equals 0, we know the power series expansion for sine of z around z equals 0. So I can write this as 1 over z times, well, sine of z is what? It's z minus z cubed over 3 factorial plus z to the 5th over 5 factorial minus dot dot dot. Right, and that is that's 1 minus z squared over 3 factorial plus z to the 4th over 5 factorial minus dot dot dot. Right, and this we have to be careful. I mean, technically our function f is not defined at z equals 0, so this is valid. So this equality is valid when z is not equal to 0, right? But we can clearly see here that this right-hand side, right, so f of z is not defined at z equals 0, but this right-hand side, this clearly is defined at z equals 0. Right, so this power series on the right-hand side clearly is the analytic function which extends our original function f across this singular point at 0. So I'll just say clearly the expression 1 minus z squared over 3 factorial plus z to the 4th over 5 factorial minus dot 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 extends f across the singular point at z naught equals 0. Another way to say it is that, and so you can define this extension also by just saying that it's f of z when z does not equal 0, and it's, well, at z equals 0, the value we want is this 1 here. So 1 when z is equal to 0. This also is the same. It's just a different way of writing this this same power series here. And so the limit of f of z as z goes to z naught is clearly this 1 here, as which you can read off from the power series. So this is definitely an isolated singularity. And so let's say this is part A. If in part B, if we look at the function g of z, which is equal to sine of z over z squared, then we can see that intuitively this has a pole at z equals 0, because what we can do is we can write this as sine of z over z over z. All right, so this function here can be, so this is analytic at z equals 0. As we can use sine of z over z, we can just, we could replace this sine of z over z with this function f tilde here, or we could just use the same sine of z over z to denote that function, and just have it understood that the value at z equals 0 is 1. So you have this analytic function at z equals 0, and its value is equal to 1, which is non-vanishing. So you can write this g of z as a non-vanishing analytic function divided by z, and this is z to the first power, right? So so this tells you that you have a pole here. So this is a pole of order 1. So you got this z to the first power there. And to explicitly see that g of z is 1 over z times this series up here. So this is 1 over z times 1 minus z squared over 3 factorial plus z to the 4th over 5 factorial minus dot dot dot. And that's 1 over z minus z over 3 factorial plus z squared over 5 factorial. Whoops, I meant z cubed or 5 factorial minus dot dot dot. And you see the Laurent expansion starts at the negative first power of that z minus 0. Okay, so those are some examples of how to tell the difference between, especially removable singularities and poles, and writing out the Laurent series around poles. All right, so now before the next definition, I need to remind you of a result from a few weeks ago, which I called the weak homotopy principle. And this says that if you have two non-intersecting typical curves and f is analytic on a domain containing the region between gamma 1 and gamma 2, then the integral of f along gamma 1 is the same as the integral of f along gamma 2. Okay, so this is proved by Green's theorem. So basically the picture is like this. There's your domain, here's your gamma 1 going around like this, and your gamma 2 is not intersecting it, it's going around like that. You just apply Green's theorem in this region in here. And that's the proof. Very simple. So that's the weak homotopy principle. And that'll be important for the next definition. And this definition connects up with the discussion from the beginning about the residue theorem. So we had some line integral, and there were some singular points inside, and we took that line integral around a big curve and turned it into a line integral around smaller curves that just went around the singular points. So this definition is going to concern those integrals around the small curves that encircle a singular point. So if f has an isolated singularity at a point z0, gamma is a typical curve whose the closure of whose interior is in the domain of f, except possibly at z0, then the residue of our function f at z0 is defined in the following way. You do 1 over 2 pi I times the integral of your function f along gamma. And so basically our picture looks like you have your domain, you have your singular point, which is at z0, and you just have some, you just have your gamma here, whoops, then your gamma is just this typical curve, and the curve and everything inside of it is contained in the domain of f, except at this center point z0. Okay, and then by the weak homotopy principle, if I take any small enough circle that's going around z0 here, the integral over that gamma is going to be equal to the integral over that small circle, because I can apply the because these two curves satisfy the hypotheses of the weak homotopy principle, and you can just apply Green's theorem on this region between the two curves. Okay, and so this definition is independent of this typical curve gamma, as long as your gamma satisfies these conditions here, then you can compute the residue using that curve gamma. But it's probably easiest to just take a small circle going around the point z0. That'll be sufficient. All right, so this is the definition of this important concept of residue of a function at a singular point. All right, so this definition in terms of integral is all well and good, and it's motivated by the discussion we had before, but we're going to see that there's a nice way to compute the residue without doing an integral. So suppose, the residue at a pole. So suppose Z0 is a pole of F, and write f of z equals k of z over z minus Z0 to the m. Right, m is greater than or equal to 1, and k is analytic. Okay, so when we have a pole, we know that we can do this. And actually, it's not necessary to assume that m is the order of the pole, as we did before. So it could be that k is 0 at Z0. We'll allow that. Okay, then the residue of f at Z0 is 1 over 2 pi I times the integral around a small circle going around Z0, and the k of z over z minus Z0 to the m, right, dz. And now the trick here is to just recognize that this looks somewhat familiar. So if I write m as m minus 1 plus 1, what I can do is remember that this actually computes a derivative of this function k. And so if I focus on this analytic function k here, so this is analytic, so I can apply Cochise theorem for higher derivatives. So this is Cauchy for higher derivatives. And what we find is that this is the m minus first derivative of k at Z0 divided by m minus 1 factorial. Okay, so this is already quite a useful formula for the residue of a function. Residue of a function at a pole. So if you have your function f written in this form, this can be a very useful formula for computing the residue. And so if we write this all out here, so k of z, so we write it in terms of a local power series. So our k is C0 plus C1 times Z minus Z0 plus dot dot dot. Right, then this quantity here, this is equal to this Cm minus 1. Right, the nth coefficient of the power series of a function is the nth derivative at the center point divided by n factorial. So that's exactly equal to that quantity there. And if we write this in terms of f, so our f of z is equal to k of z over z minus Z0 to the m. That's C0 over z minus Z0 to the m plus dot 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 plus Cm plus 1 over z minus z naught plus c, or whoops, sorry, minus 1 plus c sub m plus c sub m plus 1 z minus z naught plus dot dot dot. Right, and so we see that that the residue, and in the language we were in the notation we were using before, we called this this c naught. This was a sub negative m. This was a sub negative 1. This was a sub 0. This was a sub 1, etc. And so the residue of f at this pole z naught, this is equal to the coefficient of z minus z naught to the minus 1 in the Laurent series of f. All right, so that gives you enough to think about for now. So we have this new theorem, the residue theorem, which is kind of like Cochise theorem, except involving integrals that go around singularities, and that those integrals that go around singularities, they localize to the singular points, and those localizations to the singular points, those are called the residues of our function at the singular point. And it's so we have now here have a good method of computing the residue at a singular point that avoids integration. It just has to do with, well, in this formula, some kind of derivative of some piece of f, this k here, or we can think about it as a coefficient in a particular kind of series expansion called the Laurent series of f. All right, so much more on this later.